Alright, with multiplication and matrices down and out of our way, now we're going to be looking at what are called determinants and inverses. Now both determinants and inverses are based around the idea of the square matrix, which is, simply put, any matrix that has the same number of rows and columns. Now from our square matrices, we have a couple of unique features. We have a multiplicative identity matrix, and what this is, an n by n matrix with ones along the main diagonal and zeros everywhere else. Now what this looks like for a 2 by 2 matrix would be ones here and here with zeros elsewhere. A 3 by 3, you have a matrix that looks like this. For larger matrices, I've seen them, for instance, a 4 by 4, 1, 2, 3, and 4, with a giant 0 labeled elsewhere. And the way you can write this would be an I sub 4. Of course, you have an I sub 3. These allow you to label the fact that it's an identity, that's the I is, and then the subscript number tells how many points there are, or how many the dimensions of the square. Last is the multiplicative inverse matrix. And this is a matrix B such that A times B equals I. So if I can take two matrices and multiply them together and come up with the identity matrix, then one was an inverse of the other. So if I could do that, if A times B equals I sub n, then B is the inverse, and we write that as A to the inverse. So we're going to be working a lot in this lesson with these, and this is going to be a rather long lesson. A lot of things come out with this idea of being able to use determinants and inverses. So let's begin. First, we need to determine if these items are inverses of one another. So we're simply going to multiply them, the square matrices, row and column, and see if we come out with an identity matrix. So these first two, we're going to multiply them together. Row 1 by column 1, I have negative 4 plus 5. So row 1 by column 1, 1 times negative 4, 1 times negative 4, then 1 times 5. Next, row 1, column 2, so 1 by 1, 1 by negative 1. That will give me 1 plus negative 1. Next, row 2 with the columns. Row 2, column 1 would be 5 times negative 4, which is a negative 20, plus 4 times 5, which is 20. And then last, row 1, column 2, we have 5 times 1, which is 5, 4 times negative 1, which is negative 4. Add these together, I come out with negative 4 plus 5 is 1, then 0, 0, and 1. Since it comes out with an identity matrix, yes, these are inverses of one another. Let's try our next set. 3, 2, 5, and 6 multiplied by 2, negative 1, negative 5 halves, 3 halves. So going through and multiplying these same as before, 3 times 2 is 6, plus 2 times the negative 5 halves is a negative 5. Row 1, column 2, 3 times negative 3 times negative 1 is negative 3. 2 times 3 halves is a positive 3. Row 2, column 1, 5 times 2 is 10. 6 times the negative 5 halves is a negative 15. Then row 2, column 2, we get negative 5. And then 6 times 3 halves is 18 halves, or 9. Adding the pieces together, we come up with 1, 0, negative 5, 4. Since this does not result in a product of an identity matrix, it is not inverse. None of the are not inverses of each other, so no. So next, we're going to begin working on how to build the determinant of a matrix. So calculating determinants, which will help us to being able to build inverses and other items. If we have a 2 by 2 matrix, A, B, C, and D, the determinant of matrix A is equal to our primary diagonal as a product, A times D, minus our secondary, which is C times B. Multiply those together, the individual diagonals, and subtract them, and you'll have the determinant. So the matrix right below it, find the determinant of 3, 6, 2, and 5. I'm going to take the primary diagonal, 3 times 5, which is 15, and subtract the product from the other direction. 2 times 6 is 12, so this determinant is 3. Now, the determinant of a 3 by 3 matrix, which is as large as we're going to go in doing our calculations for this field of study, we're going to take these rows and the columns that you see here and augment them with additional pieces. So I'm going to take the first 2 columns and rewrite them. So I get A, D, G, B, E, and H. Now I'm going to multiply the products for my 3 top-down diagonals, I'll call them. So I have A, E, I plus B, F, G plus C, D, and H. I'm going to add all those together into a single sum. Next, I'm going to take the bottom-up diagonals. That'll be GEC plus HFA plus I, D, and B. Add those together and subtract them to get my determinant. So, looking at seeing what this would look like on the next one down, we have the trying to find the determinant of matrix 1, 0, 3, 2, 4, 6, 5, negative 1, 3. So I'm going to take those first 2 rows and augment them on 1, 2, and 5, 0, 4, and negative 1. First, I'm going to find the products of my top-down diagonals. So what's 1 times 4 times 3? Well, 1 times 4 is 4, and 4 times 3 is 12. To that I'm going to add my next top-down diagonal, which is 0, 6, and 5. 0 times 6 is 0, times 5 is still 0. And then my third one, what's 3 times 2 times negative 1? 3 times 2 is 6, times negative 1 is a negative 6. And then my bottom up diagonals, 5 times 4 times 3. 5 times 4 is 20. 20 times 3 is 60. To that I will add my next bottom up matrix, which is negative 1, 6, and 1. Negative 1 times 6 is negative 6, times 1 is simply negative 6. And my third, 3, 2, and 0. 3 and 2 is 6, times 0 is 0. And once I have these sums, I'm going to subtract them. So 12 plus 0 is 0. 12 plus 0 is 12, plus negative 6 is simply 6. And from that I'm going to subtract. 60 plus negative 6 is 54. 6 minus 54 is a negative 48. So the determinant of this 4 by 4 matrix is a negative 48. Takes a little bit of time to get these down, learning the patterns. It's top to bottom diagonals are positive, bottom up, we're going to subtract them together. So let's see how we can now use these determinants to apply into inverses as we go. Let's begin that with the look at an application. If you have the coordinates of the vertices of a triangle, you can use a determinant, as shown here, to find the area of that triangle. So area is 1/2 the absolute value of the determinant of a 3 by 3 matrix. The first two columns are your x and y values for the coordinates, and the third column is simply 1s, that way it doesn't change it. So, finding the area of a triangle with vertices at 1, 3, 5, 8, and 9, negative 1, we're going to say here that the area equals 1/2 the absolute value of this determinant. So let's write determinant of the matrix. So it goes 1, 3, 1, 5, 8, 1, 9, negative 1, and 1. And that's an absolute value. So we get 1/2 the absolute value of. Let's begin doing our diagonals. So first diagonal is 1, 8, and 1, which is simply 8. Second diagonal is going to be 3, 1, and it'll carry over to 9, which gives us 27. And our third diagonal will be 1, carry over to 5, and negative 1, which is a negative 5. And from that I'm going to subtract my bottom up matrices, which is 9, 8, and 1, that's 72, plus my next bottom up matrix, which is negative 1, 1, and 1, simply a negative 1. And my third is 1, 5, and 3, which gives us 15. Now with this, you'll notice that I didn't write the augmented columns, but what it simply is you're going to run out of items to multiply, and it just rolls over to the next portion. So this is going to be 1/2 of the absolute value. 8 plus 27 is 35, minus 5 is 30. And from that I'm going to subtract. 72 minus 1 is 71, plus 15 is 86. Which then becomes 1/2. 30 minus 86 is negative 56. Absolute value is 56. Half of 56 is 28. So the area of a triangle with these coordinates is 28 square units. You say, so no big deal. Well, if you are a city designer or a person looking to see what the area of a certain tract of land is, and you have a reference point, and these are mile markers in regards to that reference point, center of town, center of a field, whatever, you can find the area of it. So this could be 28 square miles worth of places to cover. If you're a crime scene investigator and person was seen at 3 different locations and body was found after a murder, you know the area that has to be covered in order to find evidences of the murder. So how can we then take this and also move forward to actually being able to find an inverse? We've had application for determinants. Now we're going to use that determinant to find an inverse matrix. So if the determinant matrix A is not 0, then the inverse of A exists. And the way we calculate it is if we have matrix A, which is values A, B, C, and D, The inverse is 1 divided by the determinant times matrix D, opposite of B, opposite of C, A. So what we did was we took our A and D values and they traded locations, and we negated B and C. Now there is a way to find the inverse of larger matrices, but that again is beyond the scope of this field of study for Algebra 2. That will come in later courses in mathematics. So let's find the inverse of this matrix 4, 2, 3, and 2. First we need to find the determinant. The determinant of matrix A equals primary diagonals 4 times 2, which gives us 8. And from that we're going to subtract our secondary diagonal, which is 3 times 2, or 6. 8 minus 6 is 2. So A inverse is 1 divided by that determinant, 2, times the matrix. Start trading my items. The primary diagonal swaps location, so I get 2 and 4 across that diagonal, and the other diagonal has the opposite signs. So 1/2 of this matrix will give us 1, -1, -3 halves, and 2. And the way we can determine if these do make a proper inverse, let's try A, or let's do that in a different color. Let's try A times our proposed A inverse, which would be row 1, column 1. So 4 times 2 is 8. 2 times -3. Oh, not -3 and not 8. I suppose it helps if I use the simplified form. So 4 times 1 is 4. 2 times a -3 halves is a -3. Next, row 1, column 2. 4 times -1 is a -4. 2 times 2 is a +4. Row 2, column 1. 3 times 1 is 3. 2 times a -3 halves is a -3. Row 2, column 2, 3 times -1 is -3. 2 times 2 is 4. Simplify these items. 4 minus 3 is 1. -4 plus 4 is 0. 3 minus 3 is 0. -3 plus 4 is 1. So we multiplied the matrices together and did come up with the identity matrix. Therefore, this is an inverse. Now let's look at an application using inverses along with the determinants. This will be our last item. Using these items, matrices can be used in banking and commerce in sending financial information over the internet. The set of data is encoded using a square matrix, and then on the receiving end it is decoded using the inverse of that matrix. And banks or financial institutions have agreements as to what their matrices are going to be for the encoding and decoding processes. If you had those items, you could intercept and decode the financial information. So they typically use matrices that are larger than 2 by 2, but you are able to go out and apply them in such a way that you can have these matrices. So we're going to begin by looking at matrix C, which is the one that we just had, 4, 2, 3, and -2. And recall that the inverse of this matrix, C inverse, was 1, -1, -3 halves, and 2. Now we're going to use this to encode a fictitious credit card number, 5469 1827 3102 9101. So what we're going to do, since we have a 2 by 2 coding matrix, we are going to take this 16-digit number and break it into 2 rows of 8. So I'm going to multiply my coding matrix by 5, 4, 6, 9, 1, 8, 2, and 7. Then 3, 1, 0, 2, 9, 1, 0, and 1. And I'm going to go through and do these products and sums rather quickly to give us our coded matrix. So 5 times 4 is 20, 2 times 3 is 6, so I have 26. 16 and 2 makes 18. 24 and 0 makes 24. 36 and 4 makes 40. 4 and 18 makes 22. 32 and 2 makes 34. I think I'm going to run out of room here. 8 and 0 makes 8. And 28 and 2 makes 30. Barely enough room. Now row 2, column 1, I got 15 and 6, which is 21. 12 and 2 makes 14. 18 and 0 makes 18. 27 and 4 makes 31. 3 and 18 makes 21. 24 and 2 makes 26. 6 and 0 makes 6. And 21 and 2 makes 23. Don't have room to end it, but this chain, 26, 18, 24, 40, 22, 34, 8, 30, 21, 14, 18, 31, 21, 26, 6, and 23, becomes the information for this credit card that gets sent over the internet. And then the inverse matrix is multiplied by it on the receiving side, and it will decrypt it back into the matrix or into the credit card number that was originally received. So the more complicated the matrix, and both the matrix and its inverse, the more difficult it's going to be to break the code and be able to come out with the information that was given. So determinants and inverses have applications and a lot of items that we're going to be using moving forward. Study this up and make sure you have it down, ready to use in our study of matrices.